Hello students, today we are going to study gradient of scalar field and its physical significance. Gradient of a scalar field. Consider a scalar field in terms of space coordinates x, y, z. Let O be the origin of the space. Consider a point P which has coordinates x, y, z in the scalar field. Let R vector be the position vector of point P that is represented by xi plus yj plus zk. What is position vector? Position vector is nothing but the distance of a point P from the origin is represented by the vector that is called position vector. Now consider another point Q which is present at the distance dr bar or dr vector from point P. So suppose x plus dx, y plus dy and z plus dz are the coordinates of point Q, and this is the position vector of point Q, which is represented by r plus dr vector plus dr vector, and dr vector is the distance from point P to point Q. Okay, and now phi, we consider phi be the scalar function or scalar quantity at point P, and phi plus d phi is the scalar quantity at point Q. Now the position vector of point P, we have given this as equation number 1, and this is the position vector of point Q, that is r vector plus dr vector is equal to x plus dxi plus phi plus dyj plus z plus dzk. Suppose this is equation number 2. Okay, what we have quoted in the diagram, now we just have to write the text. Okay, we have considered phi be the scalar quantity or scalar function at point P in the scalar field. So phi plus d phi with the value of scalar quantity or scalar function at same point, at point Q, x plus dx plus y plus dy plus z plus dz in scalar field. Okay, so therefore d phi be the change in the value of scalar quantity when going from point P to Q in the scalar field. Again, I am showing in the diagram, when we go from point P to point Q, the scalar quantity of point P, the scalar quantity at point P was phi. Okay, when we go from point P to Q, the scalar quantity would be changed to phi plus d phi. So d phi be the change in the scalar quantity when going from point P to Q. Okay, so d phi be the change in the value of scalar quantity when going from point P to Q. Now we subtract equation 1 from equation number 2. So what was the equation number 2 and equation number 1? This is the equation number 2 and this is the equation number 1. So we have we subtract equation number 1 from equation number 2. So we will get this one. Okay, r get cancelled on left hand side. Okay, we solve this bracket on right hand side. So we will get dxi plus xi plus dxi plus yj plus dyj plus zk plus dzk minus xi minus yj minus zk. So on right hand side, xi, xyi and zk will be cancelled out. Okay, then what will remain? This dxi plus dyj plus dzk will remain. So dr vector is equal to dxi plus dyj plus dzk. Suppose this is equation number 3. Now we know that phi is the scalar function, or phi is the scalar function in the scalar field. So phi is the function of xyz, because we are talking about the scalar field in 3-dimensional. So phi is equal to phi xyz. Now we will differentiate this expression by using chain rule. So what we will get d phi equal to, now first differentiate phi partially with respect to x, so del phi by del x into dx, plus differentiate scalar function phi with respect to y partially del phi by del y into dy, plus differentiate scalar function phi with respect to z partially del phi by del z into dz. So we will get this one. So this right hand side, the right hand side of this expression can be written in the form of dot product of two vectors. Suppose this one, so this can be written as del phi by del x I plus del phi by del yj plus del phi by del zk dot dxi plus dyj plus dzk. If we take this dot product between these two vectors, we will again get this. Okay, so dot product between these two vectors will get the answer of this. Okay, now we know that dxi plus dyj plus dzk is nothing but dr vector from equation number 3. This is the equation number 3. Dr vector is equal to dxi plus dyj plus dzk. So in place of dxi plus dyj plus dzk, we can write dr vector. Okay, now suppose this is equation number 4. Now the quantity in this bracket, okay, on right hand side, the quantity in this bracket or the first term is nothing but gradient of scalar field. The first term of equation number 4 is known as gradient of scalar field. So gradient of phi can be written as grad phi can be written as del phi by del xi plus del phi by del yj plus del phi by del zk. So this is nothing but gradient of scalar field. Suppose we take phi outside the bracket in multiplication outside the bracket, so we will get del phi by del xi plus del phi by del y by del by del yj plus del by del zk. Okay, so this del by del xi plus del by del yj plus del by del zk, this is nothing but del operator, or it is also called vector differential operator. Okay, this can be presented by del vector. Okay, if we put vector or we avoid this vector, okay, it is understandable that this is a del operator, and which is nothing but the vector quantity. Del is the vector quantity. Sometimes we give arrow, okay, a cap at the cap, or if we don't give arrow, then it is understandable that arrow is there because this del is nothing but the vector quantity. So gradient of phi is nothing but del phi. Okay, so this is the definition of scalar gradient of scalar function. Okay, now gradient of scalar function can be defined in one line. Del operator of scalar function is nothing but gradient of scalar field. Okay, and it is mathematically expressed as the equation number 5. Okay, del operator over scalar function is nothing but gradient of scalar field. Del operator of scalar function is gradient of scalar field. Now putting the value of equation 5 in equation 4, what is the equation 5? Putting the value of gradient of phi this in equation number 4. So in place of this we can write del phi. So d phi is equal to del phi dot dr vector. So suppose this is equation number 6. Now we have seen what is gradient of scalar field, the definition of gradient of scalar field, and expression. Now we will see next the physical significance of gradient of scalar field. So what is physical significance of gradient of scalar field? Before going through the physical significance, we consider that, okay, inside a scalar field, scalar function is same at the surface. Okay, so we'll consider a scalar field and join all the points in the field and which have same value of scalar phi. Okay, we join all the points in the scalar field and we say that at all the points the scalar function is same. So now the output surface obtained, that is nothing but the level surface. So on the level surface all the scalar values are same. So if scalar values are same, this means phi, all the values of phi are same. So displacement along the level surface when going from one point, or at all the points the scalar values are same. So going from one point to another point, the displacement along the level surface does not change phi. It means the change in phi is 0. Change in phi is 0 means d phi equal to 0. Suppose this is equation number 1. So from we have this equation from equation number 6. Okay, this we have this d phi equal to del phi dot dr from equation number 6. So from equation number 6 we have d phi is equal to del phi dot dr. Now put d phi 0, d phi is 0 from equation number 1 now. So we'll get the equation del phi dot dr vector equal to 0. means dot product of these two vector is 0. Del phi is the vector quantity, dr vector is vector quantity, so dot product between these two vector quantities is 0. Okay, so according to the properties of dot product or scalar product, when the scalar product of two vectors is 0, it means these two vectors are mutually perpendicular to each other. When two vectors are mutually perpendicular to each other, their dot product is 0. Okay, so it means that this is the dr vector, this is level surface, and del phi is nothing but the perpendicular to dr. This del phi is the vector which is perpendicular to dr. It means the angle between del phi and dr is nothing but 90. So by definition of dot product, we can write a dot b is nothing but ab cos theta. So this is a vector, suppose, and this is b vector. So its magnitude del phi, the magnitude of dr vector, is cos theta equal to 0 by definition of dot product. And here theta is 90. The angle between these two vectors is nothing but 90. Okay, if theta is 90, the cos theta is nothing but 0. Okay, so cos theta is 0, and the magnitude of this vector cannot be 0. The product of magnitudes of these vector is not 0 because cos theta is 0. So suppose this is equation number, or del phi into dr cos theta equal to 0. Suppose this is equation number 2. Okay, now next, so hence from this diagram, from this expression, we say that del phi is the vector normal to the level surface. Del phi is the vector normal to the level surface. It means that del phi, that is gradient of phi, is the vector quantity. So hence del phi is the vector normal to the level surface. Hence del phi is nothing but the vector quantity. So gradient of scalar field is a vector. So from this we got a first physical significance, that is gradient of scalar field is a vector. Okay, now we have d phi is equal to del phi dot dr from equation number 6. Okay, this equation we have. Okay, now by definition of dot product, we know that d phi is equal to the magnitude of these two vector and cos theta. Okay, so when cos theta is maximum, the maximum value of cos theta is 1. When cos theta is 1, when theta is equal to 0. So when theta is equal to 0, that cos theta is 1. Okay, so in this step we say this is the magnitude del phi into dr cos theta. Okay, we shift this dr to that side, so it will become d phi by dr equal to del phi cos theta. Okay, d phi by dr is equal to del phi cos theta. So when cos theta is maximum, the maximum value of cos theta is 1, and cos theta is 1 at the angle 0. When theta is 0, if theta is 0, then cos theta is nothing but 1 maximum. When cos theta is maximum, when angle is 0. So suppose we are considering theta is 0, so cos theta would be 1. So this above equation, if we put the value of cos theta here, so above equation will be d theta by dr is equal to del phi. Okay, when cos theta is 1. When cos theta is maximum, we'll get this gradient of scalar function, this gradient of scalar field is equal to d phi by dr. Okay, so gradient of scalar field is a vector and whose magnitude equal to the maximum rate of change of scalar function. This is the maximum rate of change of scalar function, and which is in the direction of maximum rate of change of same function. So this is the second physical significance of gradient of scalar field. Okay, so gradient of scalar field is nothing but maximum rate of change of scalar function and its direction, and directed towards the same maximum rate of change of same function. So this is the physical significance. The gradient of scalar field is a vector whose magnitude is equal to the maximum rate of change of scalar function and directed along the maximum rate of change of scalar function. So quickly we summarize that. Okay, this is the second physical significance of gradient of scalar fields. First physical significance is gradient of scalar field is a vector. Okay, and we have seen what is gradient of scalar field. Gradient of scalar field is nothing but del operator on scalar function is gradient of scalar field, and it is quoted mathematically by gradient of phi is equal to del phi. So for today, that's it. Thank you very much.